Welcome class. Myself Professor D.S. Rai, Professor Department of Civil Engineering, BBD ITM Lucknow. Today we will cover a course KCE 076 Urban Transportation Planning. This is lecture number 21 in which we will discuss trip distribution 2. Trip distribution 1 we have already covered. We will continue trip distribution in this lecture also. References that I have taken: Chakravarti Partho and Das Animesh, Principle of Transportation Engineering, Papacosta and Prede Moras, PD, Transportation Engineering and Planning, Kadiali and Lal, Principle and Practices of Highway Engineering, Naptels, and some material have been taken from internet. The content today we will cover: singly constant gravity model, Bureau of Public Road Calibration Procedure BPR, doubly constant gravity model, calibration, type of trip distribution model, intervening opportunity model, competing opportunity model, linear programming approach. So, we will take up one by one. Most of the topic of trip distribution we have covered. So, now we go ahead singly constant gravity model. Before going to start, there are many nomenclature which we are using. First is P, P means production, A means attraction, I is originating zones, J destination zone, K iteration. So, adjusted attraction factor based on AJ K is equal to AJ Cj K minus 1 into AJ K minus 1, where AJK is adjusted attraction factor for attraction zone J and iteration K. AJK minus 1 it is adjusted attraction factor for attraction zone J and iteration K minus 1. Cj K minus 1 attraction column total for zone J, iteration K minus 1. Aj desired attraction total to attraction zone J, K iteration number. Note Aj K is equal to Aj when K is equal to 1. Bureau of Public Road Calibration Procedure BPR, the technique for calibrating the form of gravity model is developed by BPR, and that is Tij is equal to Pi into Aj into Fij divided by sum over Aj into Fij, where some fraction of spatial separation of zone Dij are referred to normally as a travel time factor function and sometimes called friction factor. Doubly constant gravity model. The gravity model can be represented as Tij alpha into Pi into Aj into Fij. In a doubly constant gravity model, the sum of the trip produced between zone J I and all the destination zone J belongs to Z. This is the predicted by the model should be equal to the total actual trip ends produced at zone I. Similarly, a statement can be made for any destination zone. The above statement represent the flow conservation constant and are given as sum over j capital T I j is equal to P I, sum over I capital T I j is equal to A j. In first case, the I for all value of z, j for all value of z. The single proportionality factor alpha should be replaced by two sets of balancing factor k I and k j. So, here k I will be equal to 1 by sum over j k j into A j into F I j, and the second factor k j will be equal to 1 upon sum over I k I into A I into F I j. The flow conservation constant, the balancing factors are clearly interdependent, which suggests that the circulation of one set of balancing factor requires the value of other set. This indicates an iterative process. The classical version of the doubly constant gravity model T I j is equal to k I into k j into P I into A j into F I j, where k I and k j is the balancing factor, P I is equal to trip generated from zone I, A j trip attracted to zone j, F I j generalized function of travel cost C I j between zone I and zone j, or sometimes it is called friction factor. Now, come to the calibration. Step first, set k j is equal to 1 for all value of j. Step 2, for given k j, find k I using equation k I is equal to 1 by sum over j k j into A j into F I j. Step 3, using k I obtained in step 2, compute k j using equation k j is equal to 1 upon sum over I k I P I into F I j. Now, the fourth step, compute the trip interchange. T I j will be equal to k I into k j into P I into A j into F I j, using k I and k j obtained in step 2 and step 3 respectively. Step 5, compute the error as E is equal to sum over mode P I minus P I dash plus sum over mode A j minus A j dash, where P I is the actual production from zone I and P I dash is the estimated production from that zone for the current iteration. A j is the actual attraction towards zone j and A j dash is estimated attraction towards the zone for the current iteration. If error is not small, steps 2, 3, 4 and 5 may repeated until the error from one iteration to the next are within the acceptable limit. Now, advantage of gravity model. Based on the causal logic, trip interchange depends on trip attraction, pull and resistance friction. Recognizes that trip purpose affect trip pattern which can be solved independently for different trip types at same time of day. The next is improvement in transportation facility can be included, change in the friction. The changes in land use can be easily introduced and includes intrazonal as well as interzonal trips. So, these are the advantages of gravity models. Now, come to the general consideration of gravity model. Travel distance may vary with the trip purposes or time of day. Planner therefore must be careful while performing calibration process of gravity model. If not, it may result in overestimation or underestimation of prediction of trips. Excessive fine turning of friction factor or balancing factors may create a great deterioration and enormous prediction of future trips. Now, come to the types of trip distribution model. So, first of all, unconditioned unconstrained model, and that are sum over j T I j is not equal to P I and sum over I T I is not equal to A j. Total interaction constant model P I is equal to sum over j A j. So, T I j is equal to alpha P I into A j divided by D I j to the power n, where A is sum over I P I upon sum over I and sum over j P I into A j divided by D I j square, and this will be equal to sum over j A j by sum over I sum over j P I into A j divided by D I j square. Singly constant model. The type of trip distribution model, the production constant sum over j T I j, here T is capital T, means future forecasting trip, will be equal to P I. Attraction constant sum over j T I j is equal to A j. Doubly constant model sum over j T I j, here again T is future trip, is equal to P I j, future production in zone I, and sum over I capital T I j is equal to A z. Now, come to the intervening opportunity model. This is also a type of gravity model. Originally, the model was proposed by Stoffer in 1940. Premises a trip will remain as short as possible, lengthening only as it failed to find acceptable destination nearer at hand. The basic assumption, the number of trip interchanges is directly proportional to the number of opportunity at that destination zone and inversely proportional to the number of intervening opportunity BAC. Intervening means the things which opposes the trip. It may be in form of cost, may be in form of distance, may be in form of comfortability. Intervening opportunity model, mathematical expression are capital T I j is equal to k into A j divided by V j, where A j is equal to the total number of destination opportunity at zone j, and V j is the number of intervening destination opportunity between zone I and zone j, and k is proportionality constant to ensure that all trips with origin at zone I are distributed to the destination opportunity. Advantage of this model: intervening opportunity model distribute trips according to measures of bypass opportunity. Second, distance is used as an ordinal variable instead of a continuous cardinal one as in case of a gravity model. Logical basis in a human behavior. Limitation of this model: the idea of matrix with dimensions ranked by a distance from the origin, the nth cell of origin I is not destination n, but the nth dimension away from I, is more difficult to handle in practice. In the calibration and the application of model, the highway network is only implicitly used as in ranking different destination with their impedance. It cannot reflect the change in the roadway infrastructure. Aesthetically, gravity model performs better than intervening opportunity model. So, we can say here the gravity model is better than the intervening opportunity model, though it has a certain advantage, because intervening points have been considered in this model. Now, competing opportunity model. Basic concept: opportunity or destination compete for trip within the equal travel time, travel distance or travel cost, bands as a measure from the zone of origin. Within a given time band, every opportunity has an equal probability of acceptance. The model is based on application of probability and a set theory, similar to the comprehensed to transportation modeling. The adjusted probability of a trip ending in a zone is the product of two independent probability. The probability of a trip being attracted to a zone, the probability of trip finding a destination in that zone. Tamaginis proposed a competing opportunity model TIA, capital T here, T is capital T, IJ is equal to PI, future production zone, into P into R into AJ. Here P is the future production, R network, AJ attraction in zone J into PRS. So, computing PRAJ, the probability of attraction zone in zone J is equal to destination opportunity in zone J divided by sum of the destination opportunity available in time band up to and including M. So, PRAJ will be equal to AJ divided by sum over x is equal to 1 to M A x. PRSI is equal to probability of trip end allocation satisfaction in zone J is equal to 1 minus the sum of the destination opportunity available in time band up to and including band M divided by sum of the total destination in the study area. So, we can say PRSJ is equal to 1 minus sum over x is equal to 1 to M and A multiplied by AX divided by sum over x is equal to 1 to N AX. Here x is any time band, M time band into which J falls, AX destination opportunity available in time band X, N last time band as measured from the origin zone I. The competing opportunity model is calibrated by varying the width of the attraction time band until the trip length characteristic of the simulated trip agrees with the observed trip length frequency distribution. Further, it depends on the careful development of time band. The model is generally difficult to calibrate and has produced results that were inferior to gravity model. The use of opportunity models like growth factor method is restricted to those urban areas where no major changes in land use or transportation network are expected. Now, come to the next modeling, that is linear programming approach. A realistic objective is to minimize the total amount of travel time of trip makers in moving between origin destination pairs for a given land use allocation and a particular transportation network equilibrium state. Trip makers select origin and destination pair such that they collectively minimize the amount of travel time spent in the transportation system. So, the trip distribution problem may be formulated as expression is travel time in the system Z. The total travel time in this system Z is equal to sum over T I j subject to sum over j is equal to 1 to m T I j is equal to P I and sum over I is equal to 1 to n T I j is equal to A j. Sum over I is equal to 1 to m P I is equal to sum over j is equal to 1 to n into A j. So, T I j more than or equal to 0, A I j more than or equal to 0, P I more than or equal to 0, where T I j is the number of trip from zone I to zone j, P I the number of trip generated by zone I, A j is the total number of trip attracted in zone j, T I j is the travel time distance or cost between zone I and zone j, and n is the number of attraction zone and m is the number of generation zones. Advantage of this approach, being able to give a traffic desired line pattern, the ability to give a solution when no previous pattern is available, the ability to give the solution when a new travel pattern is to be imposed upon a city or a town for the desired efficiency of operation. A measure of efficiency of existing travel pattern or the projected by any other trip distribution model can be given. The principal disadvantage is one associated with the length and complexity of calculation required to give the solution when the number of interzonal desires is large. So, thank you very much. Thank you.